There is a world in our solar system so vast, so ancient, and so profoundly strange that even after centuries of stargazing, after decades of sending our finest machines to study it up close, we still do not fully understand it. It hangs in the darkness beyond the asteroid belt like a god of the old myths, swirling, colossal, wrapped in storms that have raged for longer than human civilization has existed. It was here before the continents of Earth had settled into their shapes. It was here before the first fish crawled onto land. It was here, quietly spinning, when the first human being looked up at the night sky and wondered what those lights were. Its name is Jupiter. And today, with the help of NASA's most sophisticated deep space probe, we are going to descend into it. Not all the way. Not yet, perhaps not ever, but deeper than we have ever gone before. This is the story of what we found there, what it tells us about the history of our solar system, what it tells us about ourselves, and above all, what it tells us about how much we still do not know. Hello and welcome to Infinite Science. I'm glad you're here. Let's begin. Before we go deeper, before we talk about what lies beneath those swirling clouds, it's worth taking a moment to truly reckon with what Jupiter is. Because numbers alone do not do it justice. Jupiter is the largest planet in our solar system, and by a margin that can make the mind stumble. Its diameter is approximately 143,000 kilometers. That is more than 11 times the diameter of Earth. But diameter is an abstract number. Let's think about it differently. If you could hollow out Jupiter and fill it with Earths, the way you might fill a jar with marbles, you could fit approximately 1,300 of them inside. 1,300 Earths. And Jupiter would still have room left over. Its mass is even more staggering. Jupiter is more than twice as massive as all the other planets in our solar system combined. Saturn, Uranus, Neptune, Earth, Mars, Venus, Mercury, all of them, their total mass, placed on one side of a cosmic scale. And Jupiter placed on the other. Jupiter wins, and it isn't close. But size is only one part of what makes Jupiter remarkable. It is also, and this is perhaps the thing that strikes observers most immediately, extraordinarily beautiful. Not in the way a sunset is beautiful, or a mountain, or an ocean. It is beautiful in the way that something immense and indifferent and ancient is beautiful. The way a galaxy photographed by a telescope is beautiful. There is no warmth in it directed at you, and yet you cannot look away. Its surface, if we can even call it that since Jupiter has no true solid surface, is a canvas of bands and swirls and whirls in shades that range from deep ochre to creamy beige, from rust red to pale gold, from smoky brown to almost white. These bands are cloud systems driven by winds that move at speeds we can barely comprehend. Hundreds of kilometers per hour. Sustained, relentless, for centuries. The planet rotates faster than any other in our solar system. Despite its staggering size, Jupiter completes a full rotation in just under 10 hours. 10 hours for a world 11 times the diameter of Earth. You can imagine what that does to its atmosphere. Stretched, spun, flattened into those distinctive bands. The equatorial region bulges outward from the centrifugal force, giving the planet a slightly squashed oblate appearance when viewed from the side. And then there is the Great Red Spot. It is a storm. That description, a storm, feels almost laughably inadequate. But let us be precise. The Great Red Spot is an anti-cyclonic storm system, meaning it rotates in the opposite direction to low-pressure storms on Earth. Its winds at the outermost edge reach approximately 450 kilometers per hour, and it has been spinning continuously without interruption for at least 350 years, perhaps longer. The first recorded observation that may correspond to the Great Red Spot was made by the Italian astronomer Giovanni Cassini in the 1660s, 3.5 centuries ago, and the storm was already there, already fully formed, already ancient when Cassini pressed his eye to his telescope for the first time. It is larger than Earth, or rather, it used to be. The Great Red Spot has been slowly shrinking over the past century. When it was first measured in detail, it spanned nearly 40,000 kilometers across, large enough to swallow 2 Earths side by side. Today, it is closer to 13,000 to 15,000 kilometers in diameter. Still massive, still larger than our home planet, but diminishing. Whether it will eventually dissipate entirely, whether one day this 300-year-old tempest will simply wind down and fade, is one of the many questions Jupiter has not yet answered. Scientists monitor it carefully. And wait. Jupiter is also home to dozens of other storms, smaller ones that still dwarf anything on Earth. White oval storms called Oval BA, nicknamed Red Junior when it briefly turned red in the early 2000s. Chains of cyclones at the poles, arranged in geometric patterns so precise they look almost engineered. Storms nested within storms. Chaos layered upon chaos, and somehow sustaining itself across millennia. It is a world of extremes, a world of violence, rendered in slow motion across a canvas the size of 1,000 Earths. And we have barely begun to understand it. But let us stay here for a moment longer, because the overview of Jupiter, the sheer physical accounting of what this world is, deserves more than a few numbers. It deserves something closer to a reckoning. Jupiter has been known to human beings for as long as human beings have looked at the sky. Before telescopes, before science, before we had any framework for understanding what the lights in the heavens actually were. Ancient Babylonian astronomers tracked Jupiter's movement across the sky with remarkable precision, recording its position on clay tablets, developing mathematical models to predict where it would be months and years in advance. Chinese astronomical records reference Jupiter going back more than 2,000 years. Greek and Roman sky watchers named it for the king of their gods, the most powerful, the most magnificent, the one who presided over the others. And without knowing anything about what Jupiter actually was, without knowing it was a planet, without knowing it had no solid surface, without knowing it could swallow 1,000 Earths, they somehow got the scale of the tribute right. They looked at that bright, steady, wandering light in the sky and understood instinctively that it commanded a kind of reverence. It is a humbling thing to contemplate. Every generation of human beings who has ever lived, from the hunter-gatherers of the ancient plains, to the philosophers of Athens, to the navigators of the Pacific, to the children sitting in classrooms right now. Every one of them has shared the sky with Jupiter. It was there on the night you were born. It will be there long after every person alive today is gone. It was circling the sun before our species existed. It will still be circling long after we are either extinct or transformed into something we could not currently recognize. There is a kind of vertigo in that thought, and a kind of comfort too. Something so ancient, so vast, so indifferent, and yet also somehow ours to study, ours to wonder about, ours to send machines to measure, to attempt to understand. That reaching toward Jupiter, that refusal to accept that the light in the sky is merely decorative, is perhaps one of the most distinctly human things we have ever done. The polar cyclones deserve a particular mention because they are among the most unexpected things Juno has found at Jupiter. When Juno first looked down at Jupiter's North Pole, a vantage point no spacecraft had ever achieved before, because earlier missions had flown past Jupiter near its equatorial plane and never managed a view of the poles. It saw something that made scientists genuinely stop and stare. The North Pole of Jupiter is covered in a roughly octagonal arrangement of cyclonic storms. 8 storms arranged around a central storm, forming a geometric pattern so regular it looks as though someone placed them deliberately. The South Pole has a similar but slightly different arrangement. A pentagonal array of 5 storms around a central one. These cyclones are enormous, each one comparable in size to the continental United States, and they have been stable in their geometric arrangement since Juno first observed them. They neither merge into each other nor drift apart. They maintain their spacing with a precision that continues to puzzle atmospheric scientists. Nothing like this exists on Earth or on any other planet we have studied. The closest analogy might be the hexagonal polar vortex on Saturn, a different kind of geometric atmospheric structure, also not fully explained. But even that is a different phenomenon. The Jovian polar cyclones are their own category of thing. A new entry in the catalogue of shapes the universe is capable of making that we had not previously suspected existed. This is what exploration does. It does not simply fill in the details of a picture we already knew. It reveals that the picture was nothing like what we thought. Here is something worth sitting with for a moment. Everything you have ever seen of Jupiter, every photograph, every painting, every image rendered by a spacecraft flying past, shows you only the very top of its cloud layer, a thin skin, a veil. What lies beneath that veil has never been directly observed by any human instrument. Think of it this way. If you were flying above Earth in an aircraft at cruising altitude, and you looked down through a thick layer of clouds, you would see the tops of those clouds, white and grey and billowing. You would have no direct way of knowing whether the ground below was ocean or desert or forest. You would be inferring, guessing, building models based on what you know about Earth in general. That is, roughly speaking, our situation with Jupiter. We see the clouds, and we infer, very carefully, very scientifically, what lies beneath. The clouds themselves are composed primarily of ammonia ice, tiny crystals that form in the upper reaches of Jupiter's atmosphere, where temperatures drop to extremely cold levels despite the planet's overall heat. Beneath those ammonia clouds, there are likely layers of ammonium hydrosulfide clouds, and deeper still, water clouds. Though the Juno mission has found intriguing evidence that Jupiter's water is distributed unevenly across the planet, concentrated in some regions, sparse in others. Why is Jupiter so difficult to study? Several reasons. Some of them are practical, some of them are almost poetic in their intractability. The first is simply the nature of the planet. Jupiter is, at its core, a world of gas and liquid. There is no surface to land on, no ground to touch down upon and set up instruments. Any probe we send into Jupiter's atmosphere is immediately subject to increasing pressure. And that pressure increases so rapidly and to such extremes that any physical probe we build will eventually be crushed long before it reaches the planet's deeper layers. We sent one probe into Jupiter's atmosphere, the Galileo Atmospheric Probe, released in 1995. It survived for approximately 57 minutes before the pressure destroyed it. In that time, it descended about 130 kilometers into the atmosphere. An extraordinary achievement, and one that taught us enormous amounts. But 130 kilometers is almost nothing compared to the full depth of Jupiter, which extends for tens of thousands of kilometers before reaching whatever lies at its center. The second challenge is radiation. Jupiter is surrounded by an intense radiation belt, charged particles trapped by its enormously powerful magnetic field. For any spacecraft orbiting Jupiter, radiation is the constant, relentless enemy. It degrades electronics, it distorts sensors, it shortens the operational life of instruments that might otherwise function for years. The third challenge is the sheer scale of what we are trying to understand. Jupiter is not a simple system. It is a dynamic, multi-layered, constantly evolving environment where the atmosphere, the magnetic field, the internal structure, and the system of moons all interact with each other in ways that are still being untangled. Understanding any one part of Jupiter requires understanding all the other parts simultaneously. A task that has occupied some of the world's finest physicists for decades. And yet, and this is the extraordinary thing about human curiosity, we keep going back. We keep finding ways to look deeper, to measure more precisely, to build instruments robust enough to survive long enough to send back just a little more data. There is a fourth challenge to studying Jupiter that is worth naming, because it is less often discussed, but equally real: the challenge of interpretation. Even when Juno sends back high-quality data, precise gravity measurements, detailed microwave profiles, careful magnetic field maps, translating that data into a picture of Jupiter's interior requires models, mathematical frameworks, assumptions about the equations of state of hydrogen and helium at pressures that we cannot fully recreate in any laboratory on Earth. And those models have uncertainties built into them, uncertainties that propagate through the analysis and mean that even our best current picture of Jupiter's interior comes with significant error bars. This is not a failure of science. It is the honest acknowledgement of what science is, a process of constrained inference where conclusions are always provisional, always subject to revision as new data arrives or as the models themselves are refined. The history of Jupiter science is full of conclusions that were later revised, sometimes dramatically, as new missions provided new data. The model of a small, compact solid core was the consensus for decades. Juno changed that. Whatever picture we now hold of Jupiter's interior is our best current understanding, and it will almost certainly be updated by future missions and future analysis. That humility, the willingness to hold conclusions lightly, to update them when evidence demands, is not a weakness of the scientific approach to Jupiter. It is its greatest strength. It is what makes science trustworthy in a way that other ways of knowing cannot match. Not because scientists are always right, but because science has built into its very structure a mechanism for finding out when it is wrong and correcting itself. Because Jupiter is not just an interesting planet, it is a key, one of the most important keys we have, to understanding how our solar system formed and how planetary systems across the cosmos come into being. And so, we built something extraordinary to help us look. The story of humanity's most ambitious attempt to understand Jupiter begins with a spacecraft the size of a basketball court, and a journey of nearly 5 years through the void of space. The Juno spacecraft was launched on August 5th, 2011 from Cape Canaveral, Florida. It carried with it the hopes and curiosity of hundreds of scientists, engineers, and researchers who had spent years designing it, arguing over its instruments, solving problems, and imagining what it might find. Juno is named after the Roman goddess, the wife of Jupiter, and, in the myth, the one capable of peering through the clouds that her husband used to conceal his mischief. It is a quietly perfect name for a spacecraft whose entire purpose is to see through Jupiter's clouds and discover what the planet has been hiding. The journey to Jupiter took nearly 5 years. Juno did not travel in a straight line. No spacecraft can, given the geometry of the solar system and the need to conserve fuel. Instead, it looped around the inner solar system, using a close flyby of Earth in October 2013 to steal a little of our planet's orbital momentum, a maneuver called a gravity assist, or gravitational slingshot, before heading outward toward Jupiter at increased speed. On July 4, 2016, Independence Day, Juno arrived at Jupiter. The arrival was, by any standard, one of the most precisely choreographed events in the history of space exploration. Juno had to fire its main engine at exactly the right moment, at exactly the right orientation, to slow itself from a speed of nearly 265,000 kilometers per hour to the point where Jupiter's gravity could capture it into orbit. If the burn was too short, Juno would fly past Jupiter and be lost forever in the outer solar system. Too long, and it might be drawn too deep into Jupiter's gravity well, into a trajectory that would eventually lead it crashing into the planet. The burn was 35 minutes long. It worked perfectly, but arrival was only the beginning. Juno's orbit around Jupiter is unusual. Most spacecraft that orbit planets do so in roughly circular paths, maintaining a relatively constant distance from the planet's surface. Juno, by contrast, orbits in a highly elliptical path, a long, stretched oval that brings it sweeping in close to Jupiter's cloud tops at its nearest point, a place called perigee, then carries it back out to a vast distance before the next swing inward. At perigee, Juno dips to within about 4,000 kilometers of Jupiter's cloud tops, closer than any spacecraft had previously approached. And it is during these brief, intense close passes that Juno does the bulk of its scientific work, its instruments firing rapidly, collecting data as fast as they can before the spacecraft swings back out again. The orbit was designed this way deliberately, not for scientific elegance, but for survival. Jupiter's radiation belts, as we mentioned, are ferocious. If Juno maintained a close orbit continuously, the radiation would destroy its electronics in a matter of weeks, perhaps days. By spending most of its time far from Jupiter, the spacecraft limits its radiation exposure and extends its operational life. But even so, even on its brief close passes, the radiation environment that Juno endures is extraordinary. The engineers who designed Juno faced a challenge that had no good precedent. Jupiter's radiation is not like anything a spacecraft normally encounters. The particles trapped in Jupiter's magnetic field are highly energetic, electrons and protons moving at speeds approaching a significant fraction of the speed of light. When these particles strike electronic components, they can flip individual bits in computer memory, degrade sensor sensitivity, and over time cause irreversible damage to circuits that the mission depends on. To protect against this, the most sensitive electronics aboard Juno are housed inside a vault, a titanium box roughly the size of a large suitcase, with walls about a centimeter thick. That centimeter of titanium reduces the radiation dose to the electronics inside by roughly a factor of 800. A remarkable engineering achievement. Juno's instrument suite includes a microwave radiometer that can penetrate far deeper into Jupiter's atmosphere than any optical instrument, measuring the thermal emission from different depths and allowing scientists to construct a picture of what the atmosphere looks like hundreds of kilometers below the cloud tops. It includes a gravity science instrument that measures tiny variations in Jupiter's gravitational field as Juno orbits, variations that reveal information about the distribution of mass deep inside the planet. It includes a magnetometer, a plasma instrument, an auroral mapper, and more. And it carries, almost as an afterthought, a small, visible light camera, JunoCam, which was included partly for public engagement purposes. The images it has produced have exceeded every expectation. Citizen scientists around the world have processed the raw data from Juno CAM into images of breathtaking beauty. Images that have appeared on the covers of magazines, in science textbooks, in art installations. Images that have made people who had never thought much about Jupiter look up from their phones and say, quietly, "Oh." Juno was originally designed for a mission of 37 orbits, after which it was expected to be deliberately deorbited into Jupiter to avoid contaminating the planet's moons. But the spacecraft has performed so well, and the science it has returned has been so rich, that NASA has extended the mission multiple times. As of our most recent information, Juno continues to operate, conducting flybys not only of Jupiter but of its major moons, Europa, Ganymede, and Io, adding dimensions to the mission that were never originally planned. It is a machine the size of a basketball court, powered by the sun at a distance where sunlight is 25 times fainter than it is on Earth. It orbits a planet so hostile to electronics that its most vital components live inside a radiation bunker. And it has transformed our understanding of the largest planet in our solar system beyond what anyone had dared to predict. Before we descend into what Juno has found, it is worth pausing to appreciate what it is like to receive data from a spacecraft at Jupiter's distance. When Juno is near Jupiter, during those brief, intense perijove passes, it is collecting data at a furious rate, filling its onboard memory with measurements from all of its instruments simultaneously. But it cannot transmit all of that data in real time. The distance between Jupiter and Earth, which varies between roughly 600 million and 900 million kilometers depending on where the two planets are in their orbits, means that radio signals, even traveling at the speed of light, take between 33 and 50 minutes to make the one-way journey. So scientists do not receive Juno's data as it is collected. They receive it hours or days later, as Juno slowly downlinks its stored measurements through its high-gain antenna, transmitting carefully across the solar system at a rate that modern internet users would find laughably slow. The data arrives in trickles. It is processed and calibrated and checked for errors. And then, gradually, painstakingly, a picture forms. There is something almost meditative about this process. In an age of instant information, of data streaming at gigabits per second, the scientists on the Juno mission have learned to receive their most precious data slowly, patiently, one carefully transmitted packet at a time. The universe does not hurry, and neither, in the end, can we. The Juno science team is large. Dozens of principal investigators and co-investigators from universities and research institutions across the United States and around the world. Each instrument on Juno has its own team of specialists who spend years learning to extract every possible piece of information from their particular detector. They argue with each other at conferences, challenge each other's interpretations in the peer-reviewed literature, collaborate on papers that synthesize results from multiple instruments into a coherent picture of the planet below. Science at this scale is not a solitary pursuit. It is a community endeavor. Sometimes a contentious one, always a collaborative one, driven forward by the shared commitment to get things as right as the data will allow. But what exactly has it found? Let's go deeper. Imagine for a moment that you are descending into Jupiter. Not in a spacecraft. No spacecraft could survive this journey. In something imaginary, something impervious to pressure and heat, something with sensors so sensitive they can detect the subtle changes in chemistry and density that mark each new layer of this alien world. You are falling through the clouds. At the very top of Jupiter's visible atmosphere, the temperature is extremely cold. around -110 degrees Celsius. You are surrounded by ammonia ice crystals. The light from the distant sun filters through the haze above you, muted and pale. Below, you can see nothing. The cloud layer you are entering is thick and opaque and extends for many kilometers. As you descend through this first cloud layer, the temperature rises. The ammonia ice crystals give way to a region where the chemistry begins to change, where ammonia and hydrogen sulfide combine to form ammonium hydrosulfide, a compound that produces thick, brownish-red clouds. The colors you see on Jupiter's surface, those deep browns and amber hues, arise partly from this region and from complex organic chemistry driven by Jupiter's internal heat and the sun's ultraviolet light above. Deeper still, if current models are correct, you would encounter a layer of water clouds, water ice and water vapor, existing at temperatures and pressures more reminiscent of a hot, pressurized industrial boiler than anything we encounter naturally on Earth. The Juno mission has provided evidence that water is indeed present in Jupiter's atmosphere, but its distribution is surprising. Rather than being spread evenly around the planet, water appears to be concentrated in the equatorial region and distributed unevenly at other latitudes. This tells us something important and still somewhat mysterious about the way Jupiter's deep atmospheric circulation works. Below the water clouds, you are now deep enough that the concepts of cloud and sky begin to lose their meaning. You are not in an atmosphere anymore, not in any sense that a human being would recognize. You are in a high-pressure gas environment where the density of the gas around you is increasing rapidly with each kilometer of descent. The temperature is rising. The pressure is rising. And you are still, by any reasonable measure, barely scratching the surface of what Jupiter truly is. At a depth of perhaps a few thousand kilometers, the gas around you has become so dense that it no longer behaves quite like a gas in any ordinary sense. It is not quite a liquid either. It is something in between, a supercritical fluid, where the distinction between gas and liquid becomes meaningless. The pressure at this point is thousands of times greater than the atmospheric pressure at the surface of Earth. The temperature has climbed to hundreds of degrees Celsius, and you are still falling. Jupiter's atmosphere. If we define atmosphere generously as the outer envelope of gas and fluid that surrounds the planet's core, is roughly 71% hydrogen and 28% helium, with trace amounts of methane, ammonia, hydrogen sulfide, water vapor, and a handful of other compounds. This composition is similar in broad terms to the composition of the Sun, a fact that is not coincidental, since both Jupiter and the Sun formed from the same primordial cloud of gas and dust roughly 4.5 billion years ago. Jupiter, in a sense, is a failed star. If it had been perhaps 70 to 80 times more massive than it is, its core pressure and temperature would have been sufficient to ignite nuclear fusion. And it would have become a star, not a planet. Our solar system would have been a binary star system. Earth, if it existed at all, would be a very different world. But Jupiter did not accumulate enough mass. It fell short of stellar ignition, and so it became, instead, the most magnificent of the gas giants, a world that bears the chemical fingerprints of a star without ever having become one. Pause for a moment on that phrase, the chemical fingerprints of a star. It is not merely poetic, it is quite literally true. Hydrogen and helium, the two elements that make up the vast bulk of Jupiter's mass, are the two most abundant elements in the observable universe. They are the elements that stars are made of. They are the elements that filled the universe in the first few minutes after the Big Bang, before any heavier elements had been forged in stellar furnaces. When we look at Jupiter's composition, we are looking at something primordial, something that connects this world to the very first moments of cosmic history. The trace elements, the ammonia, the methane, the hydrogen sulfide, the water vapor, are present in Jupiter's atmosphere in larger quantities than in the Sun. This enrichment of heavy elements relative to the Sun's composition is one of the key clues about how Jupiter formed. It tells us that Jupiter accreted material not just from the gas of the early solar nebula, but also from solid bodies, planetesimals, icy comets, rocky asteroids that brought heavier elements with them when they were captured by Jupiter's growing gravity. The balance between the solar composition gas and the enriched heavy elements is a signature of the planet's formation history, encoded in its atmosphere for billions of years, waiting for a spacecraft sensitive enough to read it. The Juno mission's microwave radiometer has been attempting to read that signature. To map the distribution of ammonia and water and other trace species as a function of depth, building a three-dimensional picture of Jupiter's atmospheric composition that goes far deeper than any previous instrument could reach. What it has found is, as so often with Jupiter, more complex than expected. The distribution of ammonia in particular has shown a puzzling pattern, with higher concentrations in some latitude bands and lower concentrations in others, that does not yet have a fully satisfying explanation. The ammonia appears to be transported by large-scale convective plumes that rise and fall through the atmosphere in ways that are still being characterized. This is the frontier of atmospheric science, not the broad strokes which are well established, but the details, which turn out to matter enormously for understanding how the planet works as a system. As we continue our imaginary descent, the layers of gas grow steadily denser and hotter. The pressure climbs into ranges that exist nowhere on Earth's surface. Pressures measured not in atmospheres, but in megabars. 1 megabar is 1 million times the atmospheric pressure at sea level on Earth. At these depths, hydrogen, the most abundant element in the universe, the simplest of all atoms, 1 proton and 1 electron, begins to behave in ways that defy ordinary intuition. And here, at this threshold of pressure and temperature, we arrive at one of the most extraordinary and least understood phenomena in planetary science. We arrive at the hydrogen ocean, not an ocean of water, not an ocean of anything we have ever touched or seen on Earth, an ocean of metallic hydrogen. Metallic hydrogen. Even the phrase sounds like something from a science fiction novel. A metal that is also hydrogen, the lightest, simplest element in the periodic table. The stuff of stars and gas clouds and the early universe. A metal. How is this possible? To understand it, we need to think about what makes something a metal. In everyday chemistry, metals are elements like iron, copper, gold, solids at room temperature with electrons that are relatively free to move from atom to atom. That free movement of electrons is precisely what makes metals conduct electricity. The electrons are not bound to any particular atom. They roam through the material, and when you apply a voltage, they flow. And that flow is what we call electric current. In a gas, including gaseous hydrogen, the electrons are generally bound to their atoms. They do not flow freely. Hydrogen gas does not conduct electricity under normal conditions. But pressure changes things. At the extreme pressures deep within Jupiter, pressures that exceed 2 to 3 million times the atmospheric pressure at Earth's surface, hydrogen atoms are squeezed so close together that their electron orbitals begin to overlap. The electrons, which in ordinary hydrogen are tightly associated with their parent proton, can no longer be said to belong to any particular atom. They become delocalized, free to roam through the material the way electrons roam through a metal. And when electrons are free to roam, the material conducts electricity. hydrogen at these pressures and temperatures becomes metallic. It becomes a liquid, electrical conductor, an ocean of conducting fluid deep within Jupiter, rotating with the planet and generating, through that very rotation and conduction, Jupiter's extraordinary magnetic field. The existence of metallic hydrogen was predicted theoretically in the 1930s by the British physicist E. Wigner and his colleague H.B. Huntington. It took decades before it could be produced in the laboratory, and even then only in tiny amounts for fractions of a second, using the shock waves produced by powerful explosives or high-powered lasers, compressing hydrogen samples to extraordinary pressures. Jupiter, however, does this naturally and at a scale that staggers imagination. The metallic hydrogen ocean inside Jupiter is estimated to be tens of thousands of kilometers deep. It contains more metallic hydrogen than exists anywhere else in the known universe. It has been there for nearly 5 billion years. And it is this ocean, this roiling, conducting, convecting sea of metallic hydrogen, that is responsible for one of Jupiter's most distinctive and important features, its magnetic field. When a conducting fluid rotates and convects, when it churns with internal currents driven by heat rising from the planet's interior, it generates electric currents, and electric currents generate magnetic fields. This process, called the dynamo effect, is the same process that generates Earth's magnetic field in our planet's liquid iron outer core. But Earth's magnetic field, impressive as it is for our purposes, is a candle flame compared to Jupiter's blowtorch. Jupiter's magnetic field is the strongest of any planet in the solar system. At the cloud tops, it is approximately 20,000 times stronger than Earth's magnetic field. It extends far into space, much farther than Earth's does, creating a vast region called the magnetosphere that encompasses all of the major Jovian moons and stretches tail-like for hundreds of millions of kilometers in the direction away from the Sun. If you could see Jupiter's magnetosphere with your eyes, if it were visible as a glowing structure against the night sky, it would appear larger than the full moon in our sky. That is how vast it is. For the Juno spacecraft, this magnetic field is both a subject of fascination and a source of mortal peril. Juno's magnetometer, which measures the precise strength and direction of the magnetic field at various points in Jupiter's orbit, has returned some of the most scientifically significant data of the entire mission. Data that has forced scientists to revise their models of how Jupiter's interior is structured. But those same magnetic field lines accelerate charged particles to tremendous energies and funnel them into the radiation belts that threaten the spacecraft's electronics. The source of wonder is also the source of danger. Jupiter, as always, gives with one hand and takes with the other. The metallic hydrogen layer is also responsible for Jupiter's striking auroras, curtains of light that appear at the planet's poles, similar in some ways to Earth's northern and southern lights, but on a scale that makes Earth's aurora look modest. Jupiter's auroras are driven by charged particles flowing along magnetic field lines and striking the upper atmosphere. But they are also fueled by material ejected by the volcanic moon Io, which injects enormous quantities of sulfur dioxide gas into the space around Jupiter, contributing to an intense plasma torus that circles the planet at Io's orbit. These auroras do not flicker and fade the way Earth's do. They are more or less continuous, a perpetual light show at Jupiter's poles, powered by the relentless combination of the planet's magnetic field, its moon's volcanism, and the ceaseless flow of the solar wind. Metallic hydrogen, then, is not merely a curiosity. It is the engine at the heart of a planetary system. It generates the magnetic field that shapes the radiation environment around the entire Jovian system. It drives the auroras. It defines the character of this world in ways that reach far beyond the cloud tops we see from afar. And we have never, not once, been able to directly observe it. Every single thing we know about the metallic hydrogen ocean inside Jupiter comes from inference, from models, from the subtle signals read by instruments orbiting at a safe distance above the cloud tops. There is something both humbling and inspiring about that. We have reasoned our way into the heart of a giant. Armed with mathematics and physics and carefully calibrated instruments, we have pulled back the veil of thousands of kilometers of crushing gas and liquid and inferred the existence of an ocean that no human eye has ever seen and no human instrument has ever touched. The laboratory experiments that have attempted to create metallic hydrogen on Earth are worth describing because they illustrate just how extreme the conditions inside Jupiter truly are. In the 1990s and 2000s, physicists at institutions including Lawrence Livermore National Laboratory and Sandia National Laboratories used powerful shock waves, generated by explosives or by intense laser pulses focused on tiny samples, to compress hydrogen to pressures of millions of atmospheres for fractions of a microsecond. In those brief instants, they detected a dramatic drop in hydrogen's electrical resistance, consistent with the transition to a metallic state. The samples then immediately expanded and returned to normal hydrogen as the shock wave passed. More recently, teams using diamond anvil cells, devices in which two industrial diamonds are used as opposing anvils to squeeze a tiny sample between their tips, have claimed to have produced metallic hydrogen at pressures of around 5 million atmospheres. These claims remain somewhat controversial in the scientific community, partly because the sample sizes are so tiny and the measurements so difficult that independent verification has been challenging. But the weight of evidence from shock experiments, from theoretical calculations, from the behavior of Jupiter and Saturn as we measure it, from spacecraft, all points in the same direction. Metallic hydrogen is real, and it exists in vast quantities inside the gas giants of our solar system. Saturn, Jupiter's slightly smaller sibling, also has a metallic hydrogen layer, and Saturn has its own remarkable magnetic field. Less powerful than Jupiter's, but still far stronger than Earth's, generated by the same dynamo mechanism. The differences between Jupiter's and Saturn's magnetic fields, and the different internal structures that produce them, are themselves a subject of intense scientific interest. By comparing the two planets, scientists hope to learn more about the conditions required for metallic hydrogen dynamos to operate, and to better constrain their models of giant planet interiors in general. That is what science is at its most profound, not just collecting data, but building a coherent picture of reality from the fragments of evidence available. Even when those fragments are incomplete, even when the picture is imperfect, even when what we find raises more questions than it answers. And speaking of questions that raise more questions, let us go deeper still. Let us talk about the core. For decades, the standard model of Jupiter's interior included a rocky or icy core at the planet's center. A dense, solid region composed of heavy elements like rock, metal, and ice, roughly equivalent in mass to 10 to 15 Earths, compressed by the weight of everything above it into a sphere perhaps the size of Earth or slightly larger. It was a tidy picture, a gas giant with a solid seed at its center, not unlike the way a pearl grows around a grain of sand. But Juno has complicated this picture substantially. When Juno measured Jupiter's gravitational field with exquisite precision, using a technique called gravity science, where tiny variations in the spacecraft's radio signal frequency, caused by variations in gravitational pull, allow scientists to map the distribution of mass inside the planet. What it found did not match the expected signature of a small, dense, compact core. Instead, the data suggested that Jupiter might have a core that is much larger than expected, but also much less dense. A core that is not compact and solid, but instead dispersed, diluted, mixed into the surrounding material over a region that might extend to nearly half of Jupiter's total radius. Scientists call this a dilute or fuzzy core, and it raises a fascinating question. How does a core become fuzzy? One leading hypothesis is that Jupiter experienced one or more giant impacts early in its history. Collisions with large planetary bodies, perhaps protoplanets the size of Earth, that crashed into the young Jupiter when the solar system was still chaotic and crowded. These impacts would have stirred Jupiter's interior, mixing material from the original compact core throughout a larger volume, creating the diffuse distribution that Juno seems to detect. Computer simulations have shown that such impacts could produce the kind of core signature that Juno measured. And given that the early solar system was indeed a turbulent, collision-filled environment, this explanation is physically plausible. But there is another possibility, even more intriguing. It may be that Jupiter's core is dissolving, very slowly, over geological time. As the extreme pressure and temperature at the planet's center gradually erode the boundary between the heavy element core and the surrounding hydrogen and helium. In this model, the fuzzy core is not the result of a catastrophic ancient impact, but of billions of years of slow, continuous mixing, a planetary blender operating on a timescale of billions of years. Neither of these explanations has been definitively confirmed. Both are consistent with the data. Both require further investigation. And there is a third possibility, which is that the truth lies somewhere between the two, or in some combination of processes that scientists have not yet fully characterized. This is how science works at its frontier. Not with clean answers, but with narrowing fields of possibility. Juno has told us what the core is not. It is not a small, dense, compact solid sphere. But exactly what it is remains a subject of active, energetic debate among the world's planetary scientists. It is worth pausing to appreciate what it means to know something about a planetary interior that no instrument has ever directly accessed. The word know does a lot of work in science, and in planetary science in particular, it covers a wide range of epistemic situations, from "we measured this directly" to "we inferred this from multiple independent lines of evidence that all point in the same direction" to "this is what our best current models predict," subject to the assumptions built into those models. The fuzzy core of Jupiter falls into the second and third categories. Juno has measured Jupiter's gravitational field with exquisite precision. That measurement is as direct and reliable as any measurement Juno makes. What the gravitational field tells us about the distribution of mass inside Jupiter is a matter of inference, and that inference depends on models of how matter behaves at extreme pressures and temperatures. Those models are very good. They are grounded in physics that has been tested in laboratory shock experiments and in theoretical calculations. But they are not perfect, and their imperfections introduce uncertainty into the inferred structure. This does not mean we should be skeptical of the fuzzy core result. Multiple independent analyses of Juno's gravity data by different teams using different modeling approaches have reached broadly similar conclusions. The internal structure of Jupiter is not what the older compact core models predicted. Something has dispersed the heavy elements more widely through the interior than expected. That conclusion is robust. The details, exactly how extended the fuzzy region is, exactly what it is composed of, exactly how it formed, those remain to be determined. Future missions might help. A more capable gravity science instrument on a spacecraft in a different orbit might produce a gravity map with even higher resolution, revealing finer-scale structures in Jupiter's interior. Seismology. The technique of using earthquake-equivalent waves to probe planetary interiors, so powerful on Earth and increasingly used on Mars through the InSight mission, might eventually be applied to Jupiter if we can find a way to detect the oscillations of the planet's atmosphere that correspond to seismic waves deep within. These so-called Jovian seismology measurements have been attempted from Earth-based telescopes with some tantalizing hints, but nothing definitive. The core of Jupiter is, in a sense, the deepest mystery in planetary science, not because it is the most exotic or the most extreme, but because it is the one that most directly encodes the history of the entire solar system, and yet remains the most stubbornly resistant to direct characterization. What we do know is that Jupiter's core, whatever its precise nature, represents a repository of heavy elements. The rocky and icy building blocks that formed in the early solar system and were incorporated into Jupiter as it grew. These elements include oxygen, carbon, nitrogen, sulfur, rock-forming minerals like silicates and iron oxides, and possibly water ice. The total mass of this heavy element region, its total enrichment relative to the composition of the Sun, gives planetary scientists crucial information about how much solid material Jupiter was able to accrete during its formation and over what timescale. And that, in turn, tells us about the conditions in the protoplanetary disk surrounding our young Sun about 4.5 billion years ago. Jupiter was not built in a day, or even in a million years. Current models suggest it took perhaps a few million years for Jupiter's rocky icy core to accumulate enough mass, perhaps 10 to 15 Earth masses, to begin gravitationally capturing the surrounding hydrogen and helium gas from the protoplanetary disk. Once it reached that threshold, however, the process accelerated dramatically. A runaway capture of gas that rapidly built the planet up to its current mass. This model, called core accretion, is the leading theory for how gas giants form. But it has never been perfectly consistent with all observations, and Jupiter's unexpectedly large fuzzy core is one more piece of the puzzle that theorists are working to incorporate. There is a rival theory worth mentioning called disk instability. In this model, Jupiter did not form gradually through the slow accumulation of solid material into a core that subsequently captured gas. Instead, the protoplanetary disk itself, the vast cloud of gas and dust surrounding the young Sun, became gravitationally unstable in certain regions, collapsing directly and rapidly into giant clumps of gas that then contracted into planets. This process, if it occurred, would have been far faster than core accretion, taking perhaps thousands of years rather than millions, and would produce a planet with a different internal structure. Less heavy element enrichment, a less distinct core, a composition closer to that of the Sun itself. The truth is that the evidence currently favors core accretion for Jupiter, but the debate between the two theories has not been fully resolved. And Juno's findings about Jupiter's actual composition and interior structure, particularly the heavy element enrichment implied by the fuzzy core, are key data points in this ongoing scientific conversation. Every orbit Juno completes, every gravity measurement it makes, is another vote cast in this debate between theories of how the universe builds its largest planets, because it speaks to just how extreme the conditions inside Jupiter are. At the very center of Jupiter, the pressure is estimated to be in the range of 40 to 70 megabars. That is 40 to 70 million times the atmospheric pressure on Earth's surface. The temperature there is believed to be somewhere between 20,000 and 40,000 degrees Celsius. For comparison, the surface of the Sun, The visible photosphere that we see when we look at it, safely with appropriate equipment, is about 5,500 degrees Celsius. Jupiter's core is significantly hotter than the surface of the Sun. That fact, stated plainly, is worth absorbing for a moment. Inside the planet we call a gas giant, named for its gaseous outer atmosphere. At its very center, there is a region hotter than the surface of our star. Jupiter contains multitudes. Let us take a moment to truly dwell in the extremity of Jupiter's interior conditions, because it is easy, perhaps too easy, to say high pressure and extreme temperature and move on, as if those phrases have conveyed something. They have not, quite. Let us try harder. The pressure at Jupiter's cloud top, at the very outermost layer we can observe, is roughly 1 atmosphere. The same pressure as at Earth's sea level. That's our starting point. As we descend, pressure increases. At a depth of a few hundred kilometers, we are already at tens of atmospheres. Deep sea divers on Earth never experience more than a few tens of atmospheres. It is, at those pressures, already dangerous to human tissue. At a depth of several thousand kilometers, we have crossed into the supercritical fluid regime. Pressures of thousands of atmospheres. No human vessel has ever experienced pressures in this range, except in specially designed laboratory equipment built specifically to explore extreme pressure phenomena. At the base of what we call the molecular hydrogen layer, still far from the center, pressures have climbed to hundreds of thousands of atmospheres. We have left behind any environment with an earthly analog. And then we cross into the metallic hydrogen layer at perhaps 2 million atmospheres. The pressure is so immense that it alters the fundamental character of matter, changes how atoms interact with each other, changes what states of matter are even possible. At the center, 40 to 70 megabars, we are in a regime that has never been recreated on Earth except momentarily, in shock experiments. The pressure at Jupiter's core is not merely high, it is categorically different from anything in human experience. And the heat. Jupiter radiates more energy than it receives from the Sun. This is a remarkable fact. The planet is losing heat. Heat generated not by nuclear fusion, as a star does, but by the slow gravitational contraction of its own mass. The same process that originally compressed the planet's core to its current state is still releasing energy, still keeping the planet warmer inside than it would otherwise be, still driving the convective currents that churn its interior and help sustain its magnetic field. The heat flowing upward from Jupiter's interior is approximately twice the amount of energy the planet receives from sunlight. That internal heat, rising through the layers and eventually escaping from the cloud tops, is what drives the enormous atmospheric circulation patterns we see. The jet streams, the storm systems, the towering convective clouds that rise from the water cloud level to the very top of the visible atmosphere. Jupiter's storms, in other words, are not driven primarily by sunlight, as Earth's weather patterns are. They are driven from below, from the Eitz planet's own interior heat, rising and escaping. Jupiter is, in a very real sense, heated from within. This has a profound consequence for the nature of Jupiter's storms. Unlike Earth's weather systems, which are ultimately powered by the differential heating of the Sun. More intense near the equator, less intense at the poles. Jupiter's storms have an additional energy source that is global and relatively uniform. This contributes to the extraordinary longevity of Jovian storm systems. There is no season on Jupiter. There is no winter to quiet the storms, no summer to restart them. There is only the relentless, perpetual outflow of ancient heat from a planet that has been cooling for 5 billion years. Juno has discovered that Jupiter's giant storms, including the Great Red Spot, extend far deeper into the atmosphere than previously believed. Rather than being shallow surface phenomena confined to the topmost cloud layers, these storms appear to have roots that plunge hundreds of kilometers deep. The Great Red Spot, Juno's gravity measurements suggest, may extend downward for perhaps 500 kilometers, a depth comparable to the distance between New York and Boston. And the jet streams, those alternating bands of eastward and westward flowing winds that give Jupiter its characteristic striped appearance, extend even deeper. Juno's microwave radiometer measurements indicate that the jet streams penetrate to at least 3,000 kilometers below the cloud tops, and possibly deeper. They are not skin-deep atmospheric features. They are deep, robust circulation patterns that involve an enormous volume of the planet's outer envelope. Below approximately 3,000 kilometers, however, Juno's data suggests that the jet streams taper off. They lose their distinctiveness, gradually merging into a more uniform rotation. Below this depth, the electrical conductivity of the gas, already beginning its transition toward metallic hydrogen, allows the magnetic field to exert a braking effect on the atmosphere, gradually damping out the differential rotation. The magnetic field, in other words, acts as a kind of coupling agent, linking the outer atmosphere to the deep interior and forcing them to rotate together, more or less as a solid body. This insight, the identification of the depth at which the jet streams terminate, and the role of magnetic braking in setting that depth, was one of the most unexpected and scientifically significant results of the entire Juno mission. And deep within, where the convective currents and the magnetic field and the metallic hydrogen ocean all interact, where pressures reach into the megabar range and temperatures soar toward tens of thousands of degrees, conditions prevail that have no parallel anywhere on the surface or in the atmosphere of Earth. Conditions that defy intuition, that can only be understood through physics and mathematics, that remain, in important respects, poorly characterized and poorly understood. It is a world of superlatives, the biggest storms, the highest pressures, the most extreme temperatures, the strongest magnetic field, the deepest jet streams. And yet, for all its violence, Jupiter is, to an outside observer, serene. The storms that would dwarf our entire planet are, from a distance of a few million kilometers, just patterns in an atmosphere. The metallic hydrogen ocean churning beneath, generating currents that move at speeds we can barely calculate, is invisible behind thousands of kilometers of cloud and gas. The pressure that would crush any machine we could build is felt by nothing. There is nothing there to feel it except the matter itself, indifferently enduring conditions that defy all human experience. If you could somehow stand outside Jupiter, truly outside, at a safe distance watching, what would you experience? You would see a sphere slowly rotating, banded in amber and cream. You would see the Great Red Spot drifting across its face like a slowly turning eye. You would see, if you had instruments sensitive enough, the auroras glowing at the poles. And you would hear nothing. Space carries no sound. The titanic violence within Jupiter produces no acoustic waves that can reach you across the vacuum. It is the most perfectly silent catastrophe imaginable. There is something philosophically interesting in this. The extremity of Jupiter's interior, the crushing pressure, the searing heat, the storms that extend for hundreds of kilometers, is not experienced by anything we know of as suffering. There is no subject within Jupiter who finds the pressure crushing or the heat intolerable. The matter simply is what it is, following the laws of physics with perfect indifference. Our awe at the conditions inside Jupiter is, in the most literal sense, our own projection. Our human frame of reference applied to a place where no human frame of reference has any purchase. And perhaps that is part of what makes planetary science so philosophically interesting. We are studying things that exist completely independently of us, that would be exactly what they are whether we existed to observe them or not, that have been behaving this way for billions of years before there were any observers, and that will continue to behave this way for billions of years after the last observer is gone. We are visitors to a universe that was not made for us, trying to understand it with minds that evolved for a very different purpose. And yet, improbably beautifully, we are succeeding, bit by bit, orbit by orbit, measurement by careful measurement. And it all happens in silence, in the absolute vacuum of space, invisible to us, unknowable except through the most indirect and ingenious of measurements. We have spoken about Jupiter's magnetic field in the context of the metallic hydrogen ocean that generates it. But the magnetic field deserves a section of its own, because it is not merely a scientific curiosity. It is an environment, a vast, invisible structure that fills the space around Jupiter for hundreds of millions of kilometers and shapes the experience of everything within it. Jupiter's magnetic field was first measured directly by the Pioneer 10 spacecraft in 1973, when it became the first human-made object to pass through the outer boundary of the Jovian magnetosphere, a boundary called the magnetopause. What Pioneer 10's instruments found astonished the scientists monitoring it from Earth. The field was enormously stronger than any planetary magnetic field previously measured. Its scale was staggering. The Juno mission has mapped Jupiter's magnetic field in higher resolution than ever before, and it has found something unexpected. Jupiter's magnetic field is not the smooth dipolar field, like a bar magnet with one north pole and one south pole, that a simple model would predict. Instead, it is complex and irregular, with significant deviation from a simple dipole. In the northern hemisphere, there is a large region near the equator where the magnetic field points inward, as in the southern hemisphere of a normal dipole field. A feature so anomalous that scientists have called it a great blue spot, in analogy to the great red spot, though it is invisible to the naked eye and exists not in the atmosphere but in the magnetic structure of the planet. This irregular magnetic field tells us something important about the deep interior. A perfectly symmetric, smooth magnetic field would be consistent with a uniform dynamo, a perfectly homogeneous, symmetrically churning metallic hydrogen ocean. The observed irregularities suggest that Jupiter's interior is not uniform, that there are asymmetries in its deep convective flows, perhaps connected to the fuzzy core structure we described in the previous section. The trapped radiation in Jupiter's magnetic field, the radiation belts, are among the most intense in the solar system. The inner edge of the radiation belt, where Juno passes on each perijove approach, contains electrons moving at a significant fraction of the speed of light. These are not the kind of electrons that power a household circuit. They are relativistic particles, carrying hundreds of times more energy per particle than the radiation inside an X-ray machine. In the vicinity of the inner radiation belt, a human being without any shielding would receive a lethal radiation dose in a matter of minutes. Even with the shielding available in current spacecraft designs, extended residence near Jupiter's inner radiation belt would rapidly destroy the most hardened electronics. Even Juno's titanium radiation vault provides only partial protection against the most energetic particles. The practical consequence of this radiation is that any future human mission to the Jovian system, if we ever send people there, would require extraordinary radiation shielding. The moons of Jupiter, particularly Europa and Ganymede, lie within the radiation belts and are themselves subjected to intense radiation bombardment. Io, the innermost large moon, receives radiation doses that would be instantly fatal to an unprotected human. Europa, slightly farther out, is still in a very hostile radiation environment. This has design implications for the robotic spacecraft we send as well. NASA's upcoming Europa Clipper mission, designed to study Europa's potential habitability, required careful engineering to survive the radiation environment through which it will fly on its repeated close approaches to the Moon. As spacecraft go deeper into the Jovian system, as we try to study Io's active volcanoes, or Europa's subsurface ocean, or Ganymede's own magnetic field, radiation management becomes one of the central engineering challenges. Jupiter gives us so much to explore, and then it surrounds that bounty with one of the most hostile radiation environments in the solar system. There is a strange beauty in the violence of Jupiter's radiation belts. The same field that accelerates particles to relativistic speeds creates those stunning auroras. The same plasma torus fed by Io's volcanoes that contributes to the radiation hazard also creates its own visible glow, observable from Earth with sensitive instruments. The forces that would destroy our electronics are also the forces that paint light across Jupiter's poles in curtains of ultraviolet glory. The way Juno maps Jupiter's magnetic field is itself a marvel of physics and engineering worth describing. As Juno orbits its onboard magnetometer, a highly sensitive instrument mounted at the end of one of Juno's 3 solar panel booms, positioned as far as possible from the spacecraft's own magnetic signature, continuously measures the strength and direction of the ambient magnetic field. Over many orbits as Juno sweeps across different latitudes and longitudes during its perijove passes, these measurements build up into a global map, a spherical harmonic model that represents the field as a sum of mathematical components at different scales. The remarkable resolution that Juno has achieved in this mapping has revealed not just the large-scale structure of the field, the overall dipole orientation, the locations of the north and south magnetic poles, but also the fine-scale features, the small-scale irregularities, the anomalies, the places where the field deviates significantly from what a simple model would predict. And it is in these fine-scale features that the secrets of Jupiter's interior are hiding, like fingerprints left in the field by the structures deep below. The Great Blue Spot, that anomalous region near Jupiter's equator where the field points in an unexpected direction, is particularly intriguing because it appears to be moving. Longitudinal drift in a magnetic anomaly is a signature of the dynamics of the conducting fluid below. The metallic hydrogen ocean is not static, and its motion carries the magnetic structures it generates along with it. By tracking how the Great Blue Spot moves over the course of Juno's mission, scientists can begin to infer something about the flow patterns in the metallic hydrogen ocean. It is as if the magnetic field is a visible tracer for currents that are otherwise entirely inaccessible to observation. A dye injected into an invisible river, making its flow briefly legible. Juno's measurements have also shown that Jupiter's magnetic field is changing over time. Not dramatically, not on human timescales, but measurably, at a rate that is consistent with the dynamics expected from a fluid dynamo in a planet that has been cooling and evolving for nearly 5 billion years. By combining Juno's measurements with those from earlier missions, Galileo, Pioneer, Voyager, scientists are building a picture of how Jupiter's magnetic field has changed over the past few decades. Extrapolating that change backward and forward in time is a window into the long-term evolution of the planet's interior. It is patient, painstaking, multi-generational science. And it is exactly the kind of work that will eventually tell us things about Jupiter that we cannot yet imagine needing to know. Jupiter does not distinguish between the beautiful and the dangerous. In this world, they are the same thing. We have spent much of our time today looking inward, diving beneath Jupiter's clouds, probing its layers, decoding its gravity field. But Jupiter is not merely a planet. It is the center of a miniature solar system in its own right, presiding over a retinue of moons that number in the dozens. And among those moons, 4 worlds that Galileo Galilei spotted with his primitive telescope in January of 1610. 4 worlds so distinct, so individually extraordinary, that they deserve a moment of our attention before we turn to the broader significance of all we have learned. These 4, Io, Europa, Ganymede, and Callisto, are called the Galilean moons, in honor of their discoverer. And in discovering them, Galileo did something that changed the history of thought. He demonstrated for the first time that not everything in the cosmos revolves around the Earth. Here were objects, clearly visible, clearly real, that orbited Jupiter, not Earth. The universe in that moment became both larger and more democratic. Let us begin with Io. Io is the innermost of the 4 Galilean moons, and it is, without qualification, the most volcanically active body in the solar system. Not just more active than Earth, which is itself a significantly volcanic planet, but more active by an order of magnitude that strains description. Io has hundreds of active volcanic centers. Its surface is continuously being reshaped by eruptions that send plumes of sulfur dioxide gas hundreds of kilometers above the surface. Its terrain is a hellscape of lava lakes, volcanic calderas, sulfur plains that shift from yellow to red to white as the sulfur cools and changes its crystalline structure, and towering volcanic peaks higher than anything on Earth. What drives this extraordinary volcanism? Not internal radioactive decay alone, as drives volcanism on Earth. Instead, Io is powered by an entirely different mechanism: tidal heating. Io orbits Jupiter in a gravitational relationship with its sibling moons Europa and Ganymede, called a Laplace resonance. For every 4 orbits Io completes around Jupiter, Europa completes exactly 2, and Ganymede completes exactly 1. This precise mathematical relationship, maintained by the interplay of the 3 moons' gravitational tugs, keeps Io's orbit slightly elliptical rather than perfectly circular. And an elliptical orbit means that Io's distance from Jupiter changes as it travels. Sometimes a little closer, sometimes a little farther. Jupiter's tidal forces, the same forces that cause Earth's oceans to bulge towards the moon, flex and squeeze Io's entire body as it moves closer to and farther from Jupiter. This constant flexing generates enormous amounts of heat through friction inside Io's interior. And that heat has to go somewhere. It escapes through volcanoes. Juno has performed several close flybys of Io, approaching to within a few hundred kilometers of its surface. The closest any spacecraft has come to the volcanic moon since the Galileo mission in the 1990s. The images returned have been extraordinary. Active volcanic plumes visible from orbit, the thermal glow of lava lakes, some of them larger than several Earth cities combined, visible in infrared. Surface features that were not present in Galileo's images, reshaped in the intervening decades by continuous volcanic activity. Io is a world in constant renewal. Its surface is geologically young, among the youngest in the solar system, because it is perpetually being repaved by new volcanic material. There are no ancient impact craters on Io, as there are on Earth's moon or on Mars, because any craters that form are quickly buried under layers of new sulfur and silicate rock. The heat generated inside Io by tidal flexing is enormous. Estimated to be roughly 2 to 3 watts per square meter of surface, which is significantly more than the heat flowing out of Earth's interior per unit area. For such a small body, Io is only slightly larger than Earth's moon. This is a prodigious outpouring of energy. All of that energy has to escape somehow, and it does so through the planet's hundreds of volcanic centers, through the slow seepage of heat, through the crust, and through the enormous lava flows that periodically erupt and cover vast areas of the surface with new material. Some of Io's volcanic features are unlike anything on Earth. Pele, one of the most famous Ionian volcanoes, has an eruption plume that reaches roughly 300 kilometers above the surface, driven not by the water vapor that powers Earth's volcanic explosions, but by sulfur dioxide gas, which vaporizes explosively when it is rapidly decompressed by a volcanic eruption. When this gas reaches space and then falls back to the surface, it deposits a ring of sulfur compounds around the vent, rings that are sometimes visible even from Earth-based telescopes as colorful, concentric patterns on Io's surface. Io's surface is also home to lava lakes, open pools of molten silicate rock that are kept liquid by the continuous volcanic activity below. Some of these lakes, particularly the one called Loki Patera, an enormous horseshoe-shaped lava lake roughly 200 kilometers across, periodically resurface themselves in a wave of overturning that spreads across the lake surface like a slow, molten tide. This resurfacing happens roughly every 1 to 2 years, with a regularity that suggests a physical mechanism, perhaps the periodic foundering of a solidified crust on the lake's surface, which sinks and is replaced by new melt from below. Juno's infrared cameras have captured this process in unprecedented detail during its recent Io flybys, giving scientists their best ever look at the dynamics of an active lava lake on another world, Europa. If Io is the most dramatic world in the Jovian system, Europa is perhaps the most consequential, because Europa may harbor beneath its icy surface a liquid water ocean, and where there is liquid water, there is, at least in principle, the possibility of life. Europa is roughly the size of Earth's moon, a little smaller in fact. Its surface is covered in water ice, smooth in some areas, fractured and complex in others. The fractures, those reddish-brown lines visible even from Earth-based telescopes, are believed to be the result of the ice shell flexing and cracking under tidal forces similar to those that drive Io's volcanism. Though, at Europa, the energy goes not into melting rock, but into keeping the subsurface ocean liquid. Beneath Europa's ice shell, which is estimated to be somewhere between 10 and 30 kilometers thick, though the precise thickness is debated, lies an ocean of liquid water. Not a small lake, a global ocean covering the entire interior of the moon, containing an estimated volume of water roughly twice the total volume of all of Earth's oceans combined. How do we know this ocean exists? We have not drilled through the ice. No probe has entered the water below. The evidence is indirect, but it is compelling. The surface features on Europa, the ridges, the chaos terrain where the ice has been broken, rotated, and refrozen in new configurations, are consistent with an active, mobile ice shell being driven by a liquid layer beneath. The distribution of these features and their ages as determined by impact crater counts suggests that the ice is indeed being churned and resurfaced from below. More compellingly, measurements by the Galileo spacecraft of perturbations in Europa's magnetic field revealed a pattern consistent with what would be produced by a salty, electrically conducting liquid beneath the surface. Consistent, in other words, with a briny ocean. Salt water conducts electricity. Fresh water does not, or barely. The magnetic signal Galileo detected from Europa tells us not only that there is likely a subsurface ocean, but that it is probably salty, chemically rich, more similar to Earth's oceans than to pure water. And at the bottom of Europa's ocean there may be a rocky seafloor, a seafloor that is in contact with the silicate rock of Europa's interior. And at the boundary between water and rock, heated by tidal forces and perhaps by residual radioactive decay, there may be hydrothermal vents, cracks in the seafloor emitting warm, chemically rich fluids into the ocean above. On Earth, hydrothermal vents in the deep ocean are among the most biologically rich environments on the planet. Life thrives there in absolute darkness, in crushing pressure, fueled not by sunlight, but by the chemical energy contained in the vent fluids. Tube worms, chemosynthetic bacteria, communities of organisms that have never seen the sun and never needed to. If similar vents exist on Europa's seafloor, and it is a significant if, but a physically plausible one, then the conditions for life, by our earthly definition, might exist there. Not guaranteed, not confirmed, but possible in a way that deserves our closest attention. This is precisely why the Europa Clipper mission, launched in October 2024, currently making its way toward Jupiter, is one of the most eagerly anticipated planetary science missions of this era. It will arrive at Jupiter in 2030 and conduct dozens of close flybys of Europa, studying the ice shell, the ocean beneath, the surface chemistry, and the Moon's geologic activity with an instrument suite, specifically designed to assess habitability. Clipper carries 9 science instruments: a camera system, an infrared spectrograph, an ultraviolet spectrograph, a magnetometer, a gravity science instrument, a plasma instrument, a radar sounder designed to penetrate the ice shell and probe its internal structure, a thermal instrument to detect regions of anomalous heat flow, and a mass spectrometer to analyze particles ejected from Europa's surface or emitted in any water vapor plumes. It is the most comprehensively instrumented planetary science mission ever sent to the outer solar system. One of the things Clipper will look for, and one of the most tantalizing possibilities in all of planetary science, is evidence of water plumes erupting through Europa's ice shell. There have been hints in data from the Hubble Space Telescope and from Galileo's archival data reanalyzed with modern techniques that Europa may occasionally vent water vapor into space through cracks in its icy surface, cracks where the tidal flexing has fractured the ice and allowed pressurized water from the ocean below to erupt outward. If these plumes exist, and if Clipper can fly through them and sample their chemistry with its mass spectrometer, it would represent an extraordinary opportunity. We could potentially learn about the composition of Europa's ocean, its salinity, its acidity, the presence or absence of organic molecules, without ever having to land on the Moon or drill through the ice. The ocean would, in a sense, be advertising its contents to us. We would only need to be in the right place at the right time with the right instruments to read the advertisement. That possibility, that an extraterrestrial ocean might announce itself through erupting plumes of water vapor, carrying chemical messages from the deep, is one of the most breathtaking ideas in the history of planetary exploration. Clipper will not land on Europa. It will not drill through the ice. But it will give us the most detailed portrait of this world we have ever had, and it may provide the crucial observations that tell us whether Europa's ocean has the chemical ingredients and energy sources necessary to support biology. Beyond Europa, we find Ganymede, the largest moon in the solar system, larger even than the planet Mercury. Ganymede is a world of ancient ice and rock, with a magnetic field of its own, the only moon in the solar system known to generate its own magnetosphere. Where this magnetic field comes from is itself a puzzle. likely involving a liquid iron core inside Ganymede, analogous to the liquid iron core that generates Earth's magnetic field. Juno has conducted a close flyby of Ganymede as well, and the images returned were extraordinary, showing detail on the moon's surface never before captured, revealing the ancient craters and younger bright-grooved terrain that tell the story of Ganymede's complex geological history. And beyond, Ganymede, orbiting at the outermost position among the 4 Galilean moons, is Callisto. Heavily cratered, ancient, its surface a record of the early solar system's violent bombardment, largely unchanged since the first few 100 million years of the solar system's history. Callisto is the most cratered body in the solar system, a world that has preserved its history in its scars, while its inner siblings have smoothed and renewed themselves. It is the quiet archivist of the Jovian family. These 4 moons, volcanic Io, icy Europa, enormous Ganymede, ancient Callisto, are not merely interesting geological objects. They are a microcosm of planetary diversity. Formed from the same cloud of material around the same planet at roughly the same time, they have evolved into 4 completely different worlds. The reasons for these differences, the gradients of tidal heating, the different distances from Jupiter, the different compositions of the material that accreted into each moon, are encoded in their surfaces and interiors, and reading them enriches our understanding of the forces that shape worlds everywhere. Jupiter, then, does not merely host one remarkable world. It hosts a system, a family, a set of laboratories in which the same physical forces play out in different registers, producing different outcomes, telling us different things about the nature of planetary bodies across the cosmos. And it is within this context, this richly interconnected, dynamically active, endlessly fascinating system, that all of the interior discoveries we have discussed play out. Jupiter is not just a planet with an interesting interior. It is the center of a world unto itself. A solar system in miniature, a place where the history of the cosmos, and perhaps even the origins of life, are written in ice and fire and magnetic fields and the slow, crushing weight of incomprehensible pressure. It is worth pausing before we speak of what these discoveries mean to appreciate how we arrived at this moment. Because the understanding of Jupiter we now possess did not arrive all at once. It accumulated, slowly, painstakingly, over more than 50 years of space exploration, through the combined efforts of thousands of scientists, engineers, mission planners, mathematicians, and the people who watched from Earth as their machines crossed the solar system and sent back signals from the void. The first spacecraft to reach Jupiter were Pioneer 10 and Pioneer 11. Twin probes launched in 1972 and 1973, respectively. They were the first human-made objects to cross the asteroid belt, a region previously thought to be potentially hazardous due to the density of debris. Pioneer 10 crossed the asteroid belt without incident, an enormous relief, and reached Jupiter in December 1973, becoming the first spacecraft ever to fly past the largest planet. What Pioneer 10 found was simultaneously familiar and alien. Jupiter's magnetic field was there as theory had predicted, but larger and more powerful than most had anticipated. The radiation belts were ferocious. Pioneer 10's instruments were pushed to their limits and partially degraded by the radiation even during its brief flyby. The atmosphere showed bands and structure consistent with what telescopes on Earth had shown, but revealed now from up close and in new detail. Pioneer 11 followed, making its own Jupiter flyby in December 1974, passing even closer to the planet and surviving the radiation environment before continuing on to become the first spacecraft to visit Saturn. then came the Voyagers. Voyager 1 and Voyager 2 were launched in 1977, designed to take advantage of a rare planetary alignment that allowed a single spacecraft to visit multiple outer planets in sequence. Voyager 1 reached Jupiter in March 1979. Voyager 2 arrived 4 months later. The images they sent back were a revelation. Nothing in prior human experience could quite prepare observers for what the Voyagers showed. Jupiter's clouds, swirling, dynamic, organized into complex patterns of jets and storms, were suddenly visible in breathtaking detail. The Great Red Spot showed for the first time its full three-dimensional character. An anticyclonic system larger than Earth, spiraling with hypnotic precision. Smaller storms, oval white shapes that orbited around the Great Red Spot's edge like boats in a harbor, were seen for the first time. And the moons. The moons were perhaps the greatest surprise. When Voyager 1 turned its cameras on Io, it saw something no one had predicted: active volcanic plumes erupting into space. One member of the imaging team, Linda Morabito, was processing a navigation image of Io's limb when she noticed an anomalous bright structure beyond the edge of the moon's disk. At first, uncertain what she was seeing, she and her colleagues gradually realized the truth: an erupting volcano. On another world, the first active volcano ever observed beyond Earth. The scientific community was electrified. The Voyagers also took the first detailed look at Europa's icy surface, the network of brown and reddish lines crossing its otherwise smooth white surface. And scientists immediately began wondering what could cause such features. The hypothesis of a subsurface ocean was not initially on everyone's lips, but the data planted a seed that subsequent analysis would germinate into one of the most exciting ideas in planetary science. The Voyager flybys lasted only a few days each, but the data they collected occupied scientists for years. The Voyager images of Jupiter remain among the most iconic in the history of space exploration. There is a human story within the Voyager missions that deserves to be told, because it captures something important about what planetary exploration actually feels like from the inside. The imaging team for the Voyager missions had to wait, sometimes for hours, as each image was slowly transmitted from the spacecraft across the hundreds of millions of kilometers separating it from Earth, received by the large dish antennas of the Deep Space Network, processed by computer, and reconstructed into a visible image on screen. In the 1970s, this process was laborious by modern standards. The images arrived line by line, built up gradually from streams of data, like a photograph, developing in a dark room. And as each new image appeared, as the swirling clouds of Jupiter resolved out of static, as the volcanic plume on Io materialized from what looked at first like a smear in a navigation image, as Europa's cracked icy surface emerged in detail never previously seen. The scientists and engineers gathered around the screens experienced something that is hard to describe in technical terms. It was the feeling of seeing, for the first time, something that no human being had ever seen before. Not a painting, not a model, not a theoretical prediction, a real place, a real world. Seen with instruments built by human hands, carried across the solar system by human ingenuity, transmitting its reality back to human minds that had never quite believed, deep down, that it would work this well. Brad Smith, the leader of the Voyager imaging team, described looking at the first detailed images of the Jovian system as feeling like being in a room where the air had been sucked out, breathless in the most literal sense. That experience, the physical sensation of awe, is not incidental to the scientific process. It is, in some sense, the engine of it. It is what drives people to spend careers on problems that may not yield answers in their lifetimes. It is the reward that no salary can replace. The Voyager missions are now more than 4 decades in the past. Both spacecraft have left the solar system entirely. They are in interstellar space, beyond the heliosphere, farther from Earth than any other human-made objects. Voyager 1 is currently the most distant human artifact in the universe. And yet the images they sent back from Jupiter in 1979 still appear in textbooks, still serve as the basis for scientific papers, still carry within them data that has not been fully analyzed. That is the legacy of great exploration. It outlasts the explorers. After the Voyagers came a long gap, a period when other missions were prioritized and Jupiter receded somewhat from the forefront of exploration. The gap was not total. Scientists continued to study Jupiter with Earth-based telescopes and with the Hubble Space Telescope, which captured remarkable images of the planet's evolving storm systems and, famously, of the Shoemaker-Levy 9 comet impact in 1994. The Shoemaker-Levy 9 event, the spectacular collision of a fragmented comet with Jupiter over 6 days in July 1994, was the first direct observation of 2 solar system bodies colliding, and it had a profound effect on public consciousness about the role of large impacts in the solar system. It also offered scientists an unprecedented opportunity to study Jupiter's atmospheric chemistry by examining what the impacts ejected from below the cloud tops, material that had never before been directly observable. The chemical species detected in the impact debris confirmed aspects of models for Jupiter's deep atmospheric composition and added new data points to the ongoing puzzle of what lies beneath the cloud deck. Then came Galileo. The Galileo spacecraft arrived at Jupiter in December 1995, and it was, by any measure, one of the most ambitious planetary missions ever undertaken. Unlike the Pioneer and Voyager flybys, Galileo entered orbit around Jupiter, the first spacecraft ever to do so, and spent nearly 8 years in the Jovian system, conducting close flybys of all 4 Galilean moons, studying Jupiter's atmosphere and magnetic field, and sending back a quantity and quality of scientific data that transformed our understanding of the system. Before Galileo entered orbit, it released a probe, the Galileo Atmospheric Probe, that plunged into Jupiter's atmosphere on December 7th, 1995, and survived for 57 minutes before being destroyed by the increasing pressure. In those 57 minutes, it measured temperature, pressure, wind speed, and chemical composition at various depths. The first, and to this day, only direct in situ measurements ever made of Jupiter's atmosphere below the cloud tops. What the probe found was both confirming and surprising. The winds in the probe's entry location were faster than expected, exceeding 500 kilometers per hour, and extended deeper than models had predicted. The chemical composition was broadly consistent with expectations for a hydrogen-helium atmosphere, but the abundances of some species, particularly helium, neon, and water, were different from what had been anticipated. Water, in particular, was found in much lower abundance than expected in the probe's entry site, a result that puzzled scientists for years and that Juno has since begun to address by mapping water distribution across the planet's equatorial region. Galileo's 8 years at Jupiter transformed our understanding of the Jovian moons as much as of Jupiter itself. Its measurements of Europa's magnetic field provided the key evidence for the subsurface ocean. Its close-up images of Io's volcanic activity revolutionized our understanding of tidal heating. Its flybys of Ganymede confirmed the existence of that moon's own magnetic field. And its extended study of Jupiter's atmosphere, radiation belts, and magnetic field laid the groundwork for the much more detailed measurements that Juno would later make. When Galileo finally reached the end of its useful life in September 2003, mission controllers deliberately directed it into Jupiter's atmosphere at high speed, ending its mission in a final plunge into the planet it had studied for so long. The decision was made deliberately to prevent any possibility of the spacecraft accidentally contaminating Europa's potentially habitable ocean should it eventually drift into that moon's orbit. And then, after another gap, during which New Horizons flew past Jupiter in 2007 and used the planet's gravity for a slingshot toward Pluto, came Juno. Juno, as we have already described, has exceeded every expectation. It has done things we did not know we needed to do. It has found things we did not know we were looking for. And it has set the stage for the next generation of Jovian exploration, Europa Clipper, JUICE, and whatever comes after them. 50 years, dozens of scientists' careers, billions of dollars in funding, thousands of engineering hours, international collaborations spanning continents and generations. And at the end of it, not an answer, but a richer, deeper, more nuanced question. A picture of Jupiter that is more complex and more wondrous than anything we could have imagined when Pioneer 10 first crossed the asteroid belt in 1972. That is the nature of exploration. You do not find what you are looking for. You find something more interesting. And you come home, changed, carrying new questions that your predecessors never thought to ask. Each mission to Jupiter has done exactly this. Pioneer arrived expecting a planet and found a radiation environment so fierce it nearly destroyed the spacecraft. Voyager arrived expecting storms and found volcanoes, active, enormous, ongoing volcanoes. On a moon no one had predicted would be geologically alive. Galileo arrived expecting to refine our models, and instead dropped a probe into an atmosphere whose wind speeds and water content defied the models entirely. And Juno arrived expecting a tidy, compact core and found a fuzzy, extended mystery that has rewritten the textbooks on how gas giants are built. At every step, Jupiter has refused to be what we expected it to be. And at every step, that refusal has been a gift. Pioneer 10 is still out there, beyond the orbit of Neptune, beyond the heliosphere, the bubble of solar wind that defines the edge of our sun's direct influence. Moving through interstellar space silently at roughly 12 kilometers per second, its nuclear power source long since exhausted, its radio silent, but still moving, still crossing the void, still carrying that small gold plaque with its simple, hopeful message. We were here, we wondered, we reached. That reaching is what brought us to this moment, and it is what will carry us to the next one. Everything we have discussed so far, the swirling cloud bands, the great red spot, the metallic hydrogen ocean, the fuzzy core, the extreme pressures and temperatures, the powerful magnetic field. All of it is intrinsically fascinating. Jupiter is a world of wonders, and those wonders would justify our study of it even in isolation. But Jupiter is not isolated. It exists in a context. And that context gives everything we have learned about it a significance that extends far beyond our solar system. To understand why Jupiter matters so profoundly to science, we need to think about what Jupiter is. In the largest sense, Jupiter is a gas giant. And gas giants, we now know, are among the most common types of planets in the galaxy. When astronomers first began discovering planets around other stars in the 1990s, using the radial velocity method, which detects the subtle gravitational wobble that a planet imparts on its star, the earliest confirmed exoplanets were almost all large, massive, gas giant planets. This was partly a selection effect. Large planets are simply easier to detect than small ones. But it was also a genuine reflection of the universe's planet-forming tendencies. Gas giants are common, and if we want to understand gas giants in other solar systems, what they are made of, how they formed, what their interiors look like, how they influence the other planets around their stars, then our best, closest, most detailed laboratory is right here, in our own solar system. Jupiter is not just a planet, it is a reference point for understanding a class of worlds that numbers in the billions across our galaxy. Consider the hot Jupiters, gas giant planets that orbit their stars at distances far closer than Mercury orbits our Sun, completing an orbit in just a few days. These planets, which were among the first exoplanets discovered, present enormous puzzles. How did they form? Did they form in the outer reaches of their solar systems, where conditions are right for gas giant formation, and then migrate inward? Or did they form in place? What does their internal structure look like, subjected as they are to intense stellar radiation? How long can they survive before their outer envelopes are stripped away? To answer these questions, we need accurate models of gas giant interiors, models that are constrained by our measurements of the one gas giant we can study in detail. Every time Juno refines our understanding of Jupiter's interior structure, it also improves the models we use to interpret the interiors of hot Jupiters around distant stars. Consider also the question of planetary formation, the precise way in which Jupiter formed, the composition of its core, the amount of heavy elements it contains, the timing of its gas capture, encodes information about the conditions in our solar system's protoplanetary disk 4.5 billion years ago. By reading Jupiter's composition and structure, we are essentially reading a historical record of what the early solar system was like. And, since protoplanetary disks around other stars should obey similar physical principles, since the same chemistry, the same physics, the same thermodynamics that shaped our solar system operate everywhere in the universe, understanding Jupiter's formation tells us something about planet formation in general across the cosmos. In fact, Jupiter's formation had a profound effect on the rest of our solar system. As it grew, its gravitational influence scattered planetesimals, the small rocky and icy bodies from which planets form, throughout the solar system. It contributed to the chaotic early bombardment that scarred the surfaces of all the inner planets, including Earth. It may have played a role in shaping the asteroid belt, both by preventing the material there from accreting into a full planet, and by sculpting the asteroid belt's structure through resonance effects that persist to this day. Some models suggest that Jupiter's early migration, it may have moved inward from its original formation location before being pushed back outward by Saturn's gravitational influence, may have had dramatic consequences for the inner solar system, including possibly contributing to the clearing of material from the region where Mars now sits, which might explain why Mars is substantially smaller than Earth and Venus. Jupiter, in a very real sense, made our solar system what it is. It is not a passenger in the story of our planetary family. It is one of the primary authors of that story. Its gravity shaped the paths of asteroids and comets. Its presence or absence may have been a determining factor in whether Earth developed the kind of stable, habitable environment that gave rise to complex life. Some scientists have proposed, controversially and without consensus, that the presence of a large outer gas giant like Jupiter may be a prerequisite for the development of complex life on inner terrestrial planets like Earth, by acting as a gravitational shield that reduces the rate of large asteroid and comet impacts on the inner planets. Others dispute this, arguing that a very large Jupiter might also redirect more comets inward, increasing the bombardment rate rather than decreasing it. The truth, as is so often the case with these large planetary scale questions, is not yet fully resolved. But the question itself, the question of whether Jupiter's presence is in some way connected to our existence, is one of the most profound questions that planetary science can ask. And this is why, when Juno sends back data about Jupiter's interior, when scientists spend their days and nights poring over gravity measurements and microwave radiometry readings and magnetic field maps, they are not simply cataloguing the features of a distant planet. They are reading a document about the history and nature of planetary systems in general, including the one that gave rise to us. There is no sharp line between understanding Jupiter and understanding ourselves in the broadest cosmic sense. Furthermore, the discoveries about Jupiter's interior have implications for the study of exoplanet atmospheres. In recent years, telescopes like the James Webb Space Telescope have begun characterizing the atmospheres of planets around other stars, measuring their chemical compositions through the technique of transmission spectroscopy, where starlight filtered through a planet's atmosphere leaves spectral fingerprints of its constituent molecules. As we detect water vapor, carbon dioxide, methane, and other molecules in the atmospheres of distant worlds, we need accurate models of how these molecules behave under high temperature, high pressure conditions. Exactly the conditions that exist in Jupiter's atmosphere at various depths. Jupiter is the benchmark. It is the ground truth against which our models of other planets' atmospheres are calibrated. Every discovery Juno makes, every piece of data it sends back, every paper published in the scientific literature analyzing its measurements, all of it ripples outward into our understanding of the universe. It connects to questions about planet formation, about atmospheric chemistry, about magnetic field dynamics, about the conditions for habitability, about the frequency of complex life in the cosmos. Consider for a moment what it means for the search for life beyond Earth. The discovery that Europa, one of Jupiter's moons, very likely hosts a global liquid water ocean beneath its ice has fundamentally changed how we think about where life might exist in the cosmos. For most of human history, the search for life beyond Earth was implicitly a search for planets similar to Earth. Rocky worlds at the right distance from their star with liquid water on the surface with a protective atmosphere. The Goldilocks zone, the habitable zone. But Europa tells us something different. Europa's ocean is not warmed by its star. It is warmed by the gravitational squeezing of tidal forces. It exists far beyond what we would traditionally call the habitable zone. And if Europa's ocean is habitable, if liquid water plus chemical energy from hydrothermal vents is sufficient to support biology, then the habitable zone is not a ring around a star. It is potentially any place in the universe where liquid water exists and energy is available, regardless of proximity to any star at all. That insight, which flows directly from studying Jupiter's moon system, potentially expands the population of places where life might exist by an enormous factor. Icy moons with subsurface oceans may exist around gas giants throughout the galaxy. Rogue planets, planets that have been ejected from their solar systems and drift through interstellar space without any star, might harbor liquid water in their interiors, kept warm by radioactive decay and tidal interactions with large moons. The universe of possible life-bearing worlds becomes vastly larger than our traditional framework suggested. We do not yet know if life exists anywhere beyond Earth. We do not even know with certainty that Europa's ocean is habitable, though the evidence for its existence is strong. But Jupiter, by hosting Europa, and by teaching us through Europa that tidal heating can maintain liquid water far from the warmth of any star, has expanded the frame of the question we are asking. And that expansion of the frame is, in science, one of the most valuable things that can happen. Furthermore, the detailed study of Jupiter's atmospheric chemistry, of how different molecular species are distributed at different depths, how convection transports material between layers, how photochemistry driven by ultraviolet light from the sun creates complex organic molecules in the upper atmosphere, gives us tools and templates that we can apply to understanding the atmospheres of exoplanets. When the James Webb Space Telescope detects methane and carbon dioxide in the atmosphere of a distant exoplanet, interpreting what those detections mean requires sophisticated atmospheric models. And those models are validated and calibrated against the one planetary atmosphere we can study in detail from orbit: Jupiter's. Every orbit Juno completes is, in this sense, not just a contribution to Jupiter science. It is a contribution to our ability to read the atmospheres of worlds we will never visit, around stars we will never approach, across distances so vast that the light we receive from them has been traveling for years or centuries or millennia before reaching our telescopes. Jupiter is not just a planet, it is a key that unlocks doors to rooms we have not even entered yet. And there are many doors still to open. We have come a long way together. We have descended in imagination and in understanding from the ammonia ice crystals at the top of Jupiter's cloud layer, through the supercritical hydrogen depths, through the luminous metallic hydrogen ocean, to the strange, fuzzy, uncertain region at the planet's core. We have witnessed storms that have raged for centuries. We have visited magnetic fields stronger than anything else in the solar system. We have watched a spacecraft the size of a basketball court weave its way around a planet 11 times the diameter of Earth, sending back data that has quietly rewritten our understanding of the largest world in our cosmic neighborhood. And yet, we do not know what is truly at Jupiter's center. We do not know whether the great red spot will persist for another century or fade within our lifetimes. We do not know the precise mechanism by which metallic hydrogen generates Jupiter's complex, asymmetric magnetic field. We do not know how Jupiter's water is distributed at depth, or why it varies so dramatically from region to region. We do not know the full story of Jupiter's formation, how many giant impacts it experienced, how much its orbit migrated in the early solar system, precisely what the protoplanetary disk looked like when this world was young. What is at Jupiter's core? Will the great red spot survive? How does the metallic hydrogen dynamo truly work? How did Jupiter shape the inner solar system? What will Juno find in the years to come? This is the nature of science at the frontier. It is not a process of answering questions and closing them away. It is a process of pushing into territory where each answer reveals the shape of the questions that lie beyond it. You climb one hill and see 3 more. You cross a river and find you are at the edge of a forest you never knew existed. Jupiter, for all that Juno has revealed, remains profoundly mysterious. And I find, and I hope you do too, that this is not a cause for frustration. It is a cause for wonder. Wonder is an interesting word, and it deserves a moment of attention. It is not the same as ignorance, the passive state of simply not knowing something. Wonder is active. It is the state of recognizing that something is unknown and feeling pulled toward it, of looking at a question and feeling, rather than discouraged, energized, of standing at the edge of what is understood and choosing, deliberately, to lean forward into the darkness rather than retreat toward the comfortable light. Scientists are often portrayed in popular culture as cold, analytical, unemotional. people who have traded away the capacity for wonder in exchange for the capacity for precision. This portrayal is almost exactly backwards. The scientists who work on Juno, who spend their careers thinking about gravity measurements and atmospheric circulation models and radiation belt dynamics, are almost universally people of deep and abiding wonder. They chose their field not despite the mysteries, but because of them. They are drawn to the questions that do not yet have answers, with the same intensity that less scientifically inclined people might be drawn to great art or great literature or great music. The universe, for them, is the source material. And it is inexhaustible. There is a particular kind of courage in dedicating a career to studying something as complex and as resistant to easy understanding as Jupiter's interior. The scientists who work on planetary interiors know that the definitive answers to many of their questions may not come in their lifetimes. The Europa Clipper mission will reach Jupiter in 2030 and conduct its flyby campaign over the following years. But even if it finds compelling evidence for habitability in Europa's ocean, the question of whether life actually exists there will likely require a lander, a sub-ice probe, and perhaps decades more of work before it can be answered. The people working on Jupiter science today are planting seeds that will be harvested by scientists not yet born, answering questions not yet formulated with instruments not yet conceived. That is the time scale of science at its most ambitious. And it requires a particular temperament, patient, curious, committed to a project larger than any individual career or lifetime, trusting that the investment of understanding will compound across generations, even if the dividends are slow to arrive. Because wonder is what brought us here. Wonder is what drove the engineers to spend years designing a radiation vault for a spacecraft's electronics. Wonder is what keeps scientists up at night, turning over gravity data in their minds, searching for the structure hidden within. Wonder is what compels us to send our finest machines billions of kilometers from Earth into the radiation belts of an alien world, to ask questions that the universe is under no obligation to answer. Jupiter has been in our skies since before we had eyes to see it. It has guided navigators and inspired mythmakers and puzzled astronomers and humbled scientists. It was a distant, wandering light for most of human history. A bright star that moved against the fixed stars, mysterious in its nature, carrying the name of the king of the gods because something about it, even to ancient eyes, conveyed a kind of kingship. Now we have been there. Not in person, not yet, but in spirit, in mathematics, in the finest machines our civilization has produced. We have circled it and probed it and measured it and mapped it. And what we have found is that the ancient awe was, if anything, not quite enough. Jupiter, understood, is more extraordinary than Jupiter merely observed. And there is more yet to come. The Juno mission continues. It is conducting flybys of Jupiter's moons, offering us new glimpses of Io's volcanic fury, Europa's icy shell, Ganymede's complex magnetic environment. Future missions are being planned and built. Europa Clipper, already launched and making its way toward Jupiter, will study Europa's subsurface ocean and assess its potential for habitability. The JUICE mission from the European Space Agency is also en route to the Jovian system, targeting Ganymede for detailed study. Each of these missions will add new dimensions to our understanding of the Jovian system. Each will raise new questions. The story is not ending, it is accelerating. There is one more thing I want to say before we close. It is something that I think gets lost sometimes in the excitement of specific discoveries. The fuzzy core, the deep jet streams, the polar cyclones. It can get lost in the technical language of megabars and metallic hydrogen and transmission spectroscopy. And it deserves to be said plainly. We are a small species on a small planet, orbiting an ordinary star in the outer spiral arm of a galaxy that contains hundreds of billions of stars. The nearest star to our own is 4 light-years away. The observable universe extends for some 46 billion light-years in all directions. By any rational measure, we are vanishingly small and cosmically brief. And yet, we have done this. We have looked at a point of light in our sky and wondered what it was. We have built instruments to look more closely. We have built spacecraft to go there. We have circled a world 11 times the size of our own and read the secrets of its interior, from the subtle variations in its gravitational field. We are a species that looks at the universe and, rather than accepting its mystery, reaches toward it. Rather than being satisfied with what we can see, we ask what lies beneath. Rather than accepting the horizon as a limit, we go over it. Or we build a machine to do so on our behalf. That is a remarkable thing, and it is worth reflecting on what that reaching costs and what it gives back. The Juno mission cost approximately $1.1 billion, a number that sounds large when stated in isolation, but which, spread across the roughly 10 years from its development to its arrival at Jupiter, amounts to something like the cost of a few hundred meters of urban highway construction per year. For that investment, we received, and continue to receive, a revolution in our understanding of the largest planet in the solar system. We received data that will inform planetary science for decades. We received images of heartbreaking beauty that have been seen by hundreds of millions of people around the world. We received answers to questions that have occupied human minds since Galileo first turned his telescope to the sky. Whether that is a good return on investment depends on what you value. But there is a case to be made, a strong case, that understanding the universe we inhabit is among the most fundamentally human things we can do with our brief time here. That the knowledge we build, the questions we ask, the methods we refine, all of it accumulates across generations into something larger than any individual mission, any individual scientist, any individual moment of discovery. Carl Sagan, the astronomer and writer who, perhaps more than anyone else in the 20th century, communicated the wonder of the cosmos to a general audience, wrote once that we are a way for the universe to know itself, that the atoms that compose our bodies were forged in stars that lived and died billions of years before our sun was born, that we are, in the most literal chemical sense, made of stellar material, and that when we look up at the stars, the universe is, in some fashion, turning its gaze upon itself. There is something in that idea that feels true, or at least feels important, that our curiosity is not separate from the universe, but part of it. That asking, what is Jupiter made of? Or what lies at its center? Or could there be life beneath Europa's ice? Are not idle questions disconnected from the fabric of reality, but expressions of the universe's own tendency towards self-knowledge, mediated through the improbable emergence of conscious, curious beings on a small blue world. We do not know if there are other such beings elsewhere. We do not know if intelligence and curiosity are common in the cosmos or vanishingly rare. We do not know if the questions we are asking about Jupiter are being asked simultaneously or in sequence by minds on worlds around other stars, minds that have their own Junos, their own equivalents of Galileo pressing his eye to a lens, their own version of the moment when a storm larger than a planet was first glimpsed from afar and found to be not just a curiosity, but a doorway. We do not know, but we wonder. And perhaps, in the grand accounting of cosmic history, wondering is enough. Perhaps the willingness to ask, to reach, to send a small machine billions of kilometers into the dark and wait patiently for its signals, is itself a kind of answer to the question of what we are. Whatever we do not know about Jupiter, and we do not know so much, we know this: we will keep asking. We will keep reaching. We will keep sending our small metal ambassadors into the hostile darkness beyond our world, and we will keep listening to what they have to tell us. And the universe, vast and ancient and indifferent as it is, will occasionally answer, not with everything, not all at once, but enough, just enough, to keep the wonder alive, just enough to make the next question worth asking. Jupiter will be there tonight if you go outside and look for it. In the right season and at the right hour, you will find it. A bright, cream-colored star that doesn't twinkle the way the real stars do. It sits steady in the sky, unwavering, because it is not a point of light, but a disk, a world, too small for the naked eye to resolve, but real and present and enormous, hanging in the darkness beyond the asteroid belt. If you find it tonight, know what you are looking at. Not just a bright dot, not just a planet, a world of metallic seas and ancient storms, a core that may be fuzzy and dissolved, hotter than the surface of our sun. A magnetic field that stretches across hundreds of millions of kilometers of space. A system of moons, volcanic, icy, ancient, enormous, orbiting in their resonant dance, keeping each other's secrets and generating each other's heat. A world that was forming while the solar system was still young, that shaped the orbits of every other planet, that may, in some indirect and profound way, have contributed to the conditions that made our own existence possible. That steady, unwavering point of light carries all of this within it. And now, you know. If this journey through Jupiter's depths has left you with a sense of wonder, if it has made you want to look up at the night sky with different eyes, then perhaps that is the most important thing we could have achieved today. The universe is not a finished story. It is a story being written, one discovery at a time, by curious minds and brave machines, and the relentless human refusal to accept that the horizon is the end. There are more worlds to explore, more mysteries waiting in the dark, more questions that will one day have answers we cannot yet imagine. We will be here exploring alongside you. If you'd like to continue this journey, if you want to be here for the next discovery, the next mystery, the next voyage into the unknown, we invite you to subscribe to Infinite Science. Every video is a new expedition. Every expedition is a new question, and the questions never stop being worth asking. Until the next one, keep looking up.